Okay, so this video is going to be about alternate form of the Fourier series that is called trigonometric form. So trigonometric form of Fourier series, that's what this video is about. Okay, and it turns out what we've been looking at for the Fourier series is exponential form because it has those complex exponential functions. Trigonometric form is going to be an alternate way to write that in terms of sines and cosines, trigonometric functions. Okay, so let me first do it by an example. So let's look at the example from the last video. That was absolute value of sine of t. Okay, so that was, we found that its Fourier series looked like this. Okay, it was e to the 2j mt divided by 1 minus 4n squared. And so like I was just saying, we actually are going to call this exponential form because it has those complex exponential functions. Okay, and whenever I say Fourier series, I typically am going to be talking about exponential form. Trigonometric form we're really not going to use too much in this course, but it is good to be aware of and can be useful sometimes. Okay, so I'm going to just first show by example how to make this sum be in terms of trigonometric functions instead of this complex exponential function. And the way I'm going to do it is I'm going to actually split up this sum into the n equals 0 term, all the terms where n is positive, and all the terms where n is negative. I'm going to do that first. So when n is 0, I just get 1 over 1. So I just have that 2 over pi plus what happens when n is positive? Well, then I'm going to have 2 over pi times the sum n is 1 to infinity of e to the 2j nt over 1 minus 4n squared. And what about when n is negative? I'm going to have 2 over pi times the sum n is negative infinity to negative 1. So that's when n is negative of e to the 2j nt over 1 minus 4n squared. Okay, so that's what I get. And now I want to try and combine the second two sums. So what can I do? Well, I can do a change of variables where I'm going to, again, I've done this, I'm going to be doing this a couple times in various places in the class. I'm going to do a change of variables and change all the n's to be negative n's. Okay, so I'll show you what I mean. So I get 2 over pi plus 2 over pi times this sum being 2j nt over 1 minus 4n squared plus 2 over pi. And now, right now, n is going over all the negative integers. So when I plug in negative integers here, right, I'm going to get negative values for n there. But I want to instead write this just so that the summation variable is actually over all the positive integers. So if we think about it, this n position here, right, before it was going to have a negative number. And so this would be like e to the 2 times j times some negative integer times t. But now I'm letting n be positive, so I should just negate the n that I have in that exponent so that I make sure I'm getting the same terms. Okay? In other words, I'm just changing all of the n's to negative n. Down here, when I have n squared, nothing really changes because n squared and negative n squared both give you the same thing. Okay, so that's just a change of variables. I'm sure you've seen it before. And what it allows me to do now is to combine those two sums into one sum. Okay, so they both have denominator 1 minus 4n squared. In the numerator, I have e to the 2j nt plus e to the negative 2j nt. Well, that numerator is sounding familiar, right? E to the jx plus e to the negative jx is just 2 times cosine of x. This is just 2 times cosine of 2nt. And now when I plug that in, what do I get? I get 2 over pi plus now 2 times cosine 2nt. I'll bring that 2 outside. So I get 2 over pi times 2, which is 4 over pi. times the sum, sorry, from 1 to infinity of cosine of 2nt divided by 1 minus 4n squared. And this denominator, right, 1 minus 4n squared, it's almost always negative, right? And so often when people have a situation like that, they want to write it so it's more obvious that it's negative. And so what we do is we're just going to multiply this denominator by -1, just switch them. So we get 4n squared minus 1. So now that's always positive, but then we're just going to put the negative outside. This is just how it's more commonly seen. Okay, but I didn't change anything from what I just had. And so there you go. So now we've written absolute value of sine of t actually in terms of a big sum of cosine. Okay, and this is going to be what we call trigonometric form, or at least for this function. This is this function in trigonometric form. Okay. But let's now say what is trigonometric form in general. Okay, so trigonometric form. That was just an example. Let's see what it is in general. Okay, and so in general, I'm going to start with some f of t in exponential form of its Fourier series. Okay, so remember this is exponential form. Exponential form. Okay, and now I'm going to go through a similar procedure as we just did to in general show how to take any Fourier series and put it into a series involving just sines and cosines, trigonometric functions. So again, I'm going to take out the 0th term, f sub 0, e to the 0 is just 1, plus, I'm going to do the sum from 1 to infinity, and then plus the rest, the sum from negative infinity to -1. Okay, I'm going to do the same thing I did above. I'm going to do a change of variables on the second sum and change all the n's to -n. So now instead of going over all the negative integers, I'm going to go over all the positive integers. But now I got to change everywhere I see an n to a -n. But that allows me now to combine these sums. Okay, so now I get f sub n e to the j n omega naught t plus f sub -n e to the negative j n omega naught t. Okay. Now what can we do? Well, now we can use Euler's formula and just turn these exponential functions into sines and cosines, right? So I'm going to get, I know it's a lot of terms, but it'll kind of simplify in the end a little bit. So we're going to get f sub n. Now e to the j n omega naught t is just cosine of n omega naught t plus j sine of n omega naught t plus f sub -n. What is e to the negative j n omega naught t? Well, e to the negative jx is really just e to the j times -x, which by Euler's formula is cosine of -x plus j sine of -x. And now we know cosine is an even function, so cosine of -x is just cosine of x. Sine is an odd function, so sine of -x, I bring that negative outside. I get minus j sine of x. Okay, so e to the negative jx is just cosine of x minus j sine of x. Okay, so that's a good thing to remember. I'm going to use that right now. And I get cosine of n omega naught t minus j times sine of n omega naught t. Okay, that was just expanding that term right there. Now what can I do? Well, now out front, I'm going to do a thing that doesn't quite look right. Okay, I'm going to do 2 times f sub 0 divided by 2, and you'll see why in 1 second. We're going to make a substitution. Just so happens that's going to work out nicely for us. It's just kind of the convention what people do. You'll see why in a second. And now I'm going to combine some terms in the sum. Okay, so what do I have that's multiplying cosine? Well, I have f sub n plus f sub negative n multiplying cosine of n omega naught t. And then what do I have multiplying sine? Well, I have f sub n times j plus f sub negative n times negative j. So all in all, that's j times f sub n minus f sub negative n times sine of n omega naught t. Okay, and now I'm going to finally write this equal to how you'll typically see it. So I'm going to call that a sub 0 over 2 plus the sum, n is 1 to infinity, of a sub n cosine of n omega naught t plus b sub n sine of n omega naught t. Now I got to tell you what those constants are, where a sub n is going to be f sub n plus f sub negative n, and b sub n is j times f sub n minus f sub negative n. Okay, and so now you can see why we had to divide by this too, because when I plug in 0 for n, a sub 0 is f sub 0 plus f sub negative 0. So it's just 2 times f sub 0. So when I divide by that 2, I get back f sub 0, which is what I wanted. Okay, so it looks a little awkward here, but it makes this description a little nicer. And so there you go. So that is the trigonometric form right here at the bottom. This is our trigonometric form for the Fourier series, because you can see that it's now a summation of a bunch of coefficients, a sub n's and b sub n's, but now just multiplying trigonometric functions instead of those complex exponentials. You can see these coefficients can certainly still be complex. Okay, it's not like we've somehow gotten rid of the complex numbers, but at least now it's in terms of sines and cosines, okay, which sometimes you might want for various reasons. All right, so let's do one more example here. Okay, I have a sawtooth wave where we're going to find the exponential and trigonometric forms. Okay, we just got a couple pages left here. Okay, so I'm going to have my f of t function. It's going to be a sawtooth wave, which just kind of looks like this. And it's going to be periodic, of course. And it's going to have height 1, and the period is just going to be 1. Right? I just shift by 1 and I get back the same function. So we can see that the period is 1 and the fundamental frequency is omega naught, which is 2 pi OA period. It's in this case just 2 pi. Okay, and I'm also going to note up front that f of t just equals t when t is in the interval 0 to 1. So in this range, f of t just equals the function t. It just has slope 1. And we're going to use that when we're finding the coefficients right now. Okay, so what we're going to do is find the Fourier series for f of t in exponential and trigonometric form. Okay, so I'll just write the exponential form down so we can remind ourselves what it is. Okay, and now we got to find those Fourier series coefficients. Okay, and there's no easy way to take our function and express it immediately in terms of complex exponentials like there was for, say, cosine. So we have to use the integral here. So the Fourier series coefficient f sub n, we know equals this integral. Okay, so what is t for us? T is just 1. So I'm just going to have 1 over 1. Now an integral, where should I, what interval of length 1 should I integrate over? Well, this note is kind of hinting at us, probably just choose 0 to 1. That looks like a natural interval to integrate over, because on that interval, what does f of t equal? Just t. right? It just equals the function t on that interval. So that's nice. So e to the negative j n omega naught t dt. Okay, so that's where we're at. And now we're going to cite a fact from calculus that you can verify quickly on your own. I just don't want to waste time in the video doing this. So from calculus, okay, this is integration by parts. You can try this on your own for practice. It's not too bad. Okay, what happens when I have an integral like this of t e to some constant times a dt? Well, just apply integration by parts and you'll see that equals 1 over a times t minus 1 over a e to the at. Okay, so this is just a calculus fact you can verify on your own. Okay, so in our case, we're going to use a equals what? It's right there. Oh, and what was omega naught? Omega naught was 2 pi. So I'll even just plug that in right now. 2 pi nt. Okay, so we're going to use a as negative j 2 pi n. Okay, all right. So when that happens, okay, now we're going to plug in for what that integral equals right here. We're going to get 1 over a is negative j 2 pi n. Okay, t minus 1 over negative j times 2 pi n e to the negative j 2 pi nt. Okay, we want to evaluate that from 0 to 1. And the other thing we have to notice is, wait a second, n could be 0, right? 0 is an integer. So this line is only valid when n does not equal 0. And we'll go back afterwards and consider the case when n equals 0 later. All right. So this is what we have. Now I have to plug in for the different values of t. So I'm going to have this. Now what do I get? When I plug in t equals 1, I'm going to get 1 minus 1 over negative j 2 pi n e to the negative j 2 pi n times 1. Okay, minus what I get when I plug in 0. And that's just going to be 0 minus 1 over negative j 2 pi n. And then e to the j0 is just 1. So that's all I get. And what about this term here, e to the negative j 2 pi n? On the complex plane, that's just going around the unit circle an integer number of times, right? Integer times 2 pi. For my angle, I'm always going to get back to 1. So that number right there just equals 1 for all n. For all integer n. Okay, so what do I end up getting? I end up getting 1 over negative j 2 pi n times 1 minus 1 over negative j 2 pi n. And then over here, well, I mean times 1, and then minus minus, so plus 1 over negative j 2 pi n. Look at that, those two terms cancel. And I'm just left with 1 over negative j 2 pi n for my Fourier series coefficients. And you can also write that as j over 2 pi n if you want. Okay, so that's nice. That's a nice simple expression for my Fourier series coefficients, but that was only when n wasn't 0. What about when n equals 0? Let's just consider that case real quick. It's pretty easy. We just need the 0th Fourier series coefficient. I can just go back to the beginning and plug in 0 for n straight away. So I'm just going to get the integral from 0 to 1 of t times e to the 0, which is 1. This is just t squared over 2 from 0 to 1, and so I just get a half. Okay, so f sub 0 is a half, and f sub n equals j over 2 pi n for any non-zero n. Okay, so what does that tell us? So that tells us our f of t function equals the sum f sub n e to the j 2 pi nt. Okay, and now I'm going to write this in exponential form. So I'm just going to take the 0 term out. So when n is 0, I get f sub 0 times 1. F sub 0 is just a half. Plus, now I'm going to sum over all the rest. So the way we can write that is n is negative infinity to infinity. And I'll just say n is not 0 in the sum. Okay, so go over all the integers except 0. And what do I get then? Well, then I want to plug in for these Fourier series coefficients, which I have right here. You can see that the j over 2 pi doesn't depend on n, so I'll bring that out. Now what I have left is just e to the j 2 pi nt divided by n. Okay, so there is the exponential form. The exponential form of our Fourier series. Okay, but we also wanted the trigonometric form. And at this point, you could just use the formula up here. You could plug in and find these a sub n's and b sub n's, and you would get the trigonometric form. But just for practice, I'm going to go through the process again, just so we understand all the steps. Okay, so I'm actually going to do this by hand again. So let's do 1/2 plus. And now what I'm going to do is split the sum up just as we've been doing. So I have j over 2 pi. Now I'm going to have the sum from n equals 1 to infinity, all the positive n's, e to the j 2 pi nt over n, plus the sum, n is negative infinity to negative 1, all the negative n's, e to the j 2 pi nt over n. Okay, now I'm going to do the same thing I've done every time. I'm going to do a change of variables, change all the n's to negative n's in the second sum. Okay, and when I do that, I'll be able to combine these sums. So what am I gonna get? I'll get e to the j 2 pi nt over n from the first sum. And then I'm going to add to that what I get when I plug in negative n for all these n's, which is e to the negative j 2 pi nt over negative n. So this is my situation. I don't need these outer params. So that's what I get. And now I can combine those two terms in the second sum. And it's going to be 1 to infinity. And what do I get? I get e to the j 2 pi nt minus e to the negative j 2 pi nt all over n. And what does that numerator remind us of? Well, it should remind you of sine, right? This is just 2j times sine of 2 pi nt. Okay, pretty nice. So when I plug that in, here we go, we're just about done. When I plug that in for the numerator, I'll get a 2. That'll cancel this 2 outside. And this j combined with that j will give me a negative 1. So I'm going to get negative 1 over pi times the sum, n is 1 to infinity of what? I'm going to get sine of 2 pi nt divided by n. Okay, and there we go. That is our trigonometric form. For the Fourier series, because it's just expressed in terms of sines in this case, not even cosines. And we can check that with what we got up above. We can say, all right, well, the thing multiplying the cosines is going to be f sub n plus f sub negative n. And what happens when we take our f sub n and add it to f sub negative n plus j over 2 pi negative n? We can see they exactly cancel. We get 0, right? And that's good because we don't have any cosines in our expression. All these terms are 0. And you can check that this term is correct, right? A sub 0 is just f sub 0 times 2, which is 1/2. And then we divide it by 2, right? So 2 times 1/2 divided by 2 is just 1/2. And so our 1/2 is correct as well. And then finally, what about the coefficients? What about the coefficients in front of sine? Okay, we're going to have j times f sub n minus f sub negative n. Let's see what that would be. So j times f sub n, j over 2 pi n minus f sub negative n, j over 2 pi times negative n. What am I going to get? Well, I get a negative times a negative, so I'm just going to get 2 times j over 2 pi n. So that's going to give me j over pi n. And the j's give me a negative 1 over pi n. Those should be the coefficients multiplying my sine. And sure enough, they are, right? Negative 1 over pi n, negative 1 over pi n. Okay, so everything checks out with what we did in general, but I did want to just show going through the process one more time so we can get the hang of it all from scratch. Okay, so yeah, so that is another form of the Fourier series. And that's all I had for this video. I will see you in the next one.